Okay, next section is about Newton's law for rotation. Okay, and we are going to practice what we did. We are just like kind of laying out the concepts first. And to understand, to be able to apply Newton's law, first of all, we need to understand the torque concept. And this concept is probably one of the more challenging concepts because it has more math in it. We even need to understand, we will talk about some extra math like cross product, right hand rule, to be able to understand torque. Okay, so we did discuss torque very briefly to understand the center of mass section in chapter 9. Now we need to understand all the details about torque. Okay, and this torque is also called moment, especially when you take like statics. That's going to be the way that you will see this concept, but it is very important. Okay, so what do we have here? If you look at the picture, we have some sort of a mass. It's in the form of a straight line. Let's call it a beam. So we have a beam, that's the object. One end is on a pivot point, as you can see it on the left side of the figure. And on the other hand, we are applying a force F from the other end with an angle theta from the horizontal. So a couple things that we are going to define. One of the most important things are, where is the pivot point? Pivot point is the point that you fixed your object at that point. So if there's any rotation, it's going to be around this point at the pivot point. Okay, it's also called fulcrum. That is the fixed point, and the rotation axis is passing through the pivot point. And again, that's like kind of like in the motion problem, we need to show where the origin is, right? That this is kind of that, like you need to know where the pivot point is. Okay, because you need to draw a position vector, and it's called R. It's also known as moment arm, since torque is moment, and this is the moment arm. What is that? It is the position vector from the pivot point to the force point. So you start from the pivot point, as you can see on the figure, and then go through the force point and draw your vector. Okay, and that is called moment arm, R, and that's the vector. It's a position vector. So you start from the pivot point, go all the way to the force point, and you have the force, right? And then you have the angle theta. So I'm also going through this items on the notes. Theta is the angle between R and F, because you can see that F is this way and R is this way, and the angle between them is that, theta. So you just need to really be able to see what is the angle between R and F, okay? Just like that, we did it for work done, right? We talked about dot product. It was F dot D, and we needed to find that angle between those two, but we did the dot product. So that was dot product. This is not going to be the dot product. We'll talk about that. And that F has two components. We are calling it FR and FT, and FR is the radial component, FT is the tangential component, very similar to the velocities and accelerations that we discussed earlier. So what is FR? FR is the component of F along R, so that's why it's called radial component. And in the form of F, looking at this vector, if you resolve the components, you get F cosine theta for FR, right? Hopefully that's clear, because that angle is adjacent to FR, so it's going to take the cosine function. And on the other hand, FT, the tangential force, is going to take the theta in the form of sine theta, right? And it is FT is equal to F sine theta. Okay, so those are the components. Simple vector algebra there, resolving the components. And the component Ft, the tangential component of the force, is what causes the rotation about the pivot point. So at this point, I want you to think something. Like, think about how you open a door. also kind of investigate where kind of observe where the handle is, where's the pivot point. And this case is somewhat similar to that, but you're looking from the top view, okay, not directly to the door, but you're looking at from the top view, and the pivot point is where the hinges are, and the handle is on the other side, right? And when you open the door, you can use this tangential force. You're pulling the door toward yourself, right, kind of perpendicularly against the door's surface, and so you can open the door. So that, because you can rotate the door that way. But if you apply a force along the whole handle, maybe on both sides of the door, and then kind of pull it like this, the radial force, okay, you cannot rotate the door, right? So that force has no ability to rotate the door, but the tangential one has the ability to rotate the object or the door. So the tangential one is the one that has torque then, because torque is the ability to rotate the object by a force, okay? And only the tangential force has that. And when you look at it, that means the component of force which is perpendicular to the moment arm, this R here, will have an ability to rotate the object. Okay, will have a contribution to torque or moment. Okay, so I'm gonna repeat the last three items that I'm talking about. The component of the tangential component of F is what causes rotation about the pivot point. The ability to rotate the object depends on the value of tangential force and the distance r, that's the moment arm. And the magnitude of the torque created is given by r times ft, because these are perpendicular to each other. But ft is what? F sine theta, right? Put that in. It becomes rf sine theta. So for a given r, the torque is largest when F is perpendicular to R. So if you do this and you're pulling the object in this shown force vector here, F. Okay, so let's get rid of a couple things here. So if you're really pulling it this way to be able to rotate this object, you're really using some of your force for nothing. Okay, you don't need to apply that much force. Because only this component will rotate. So instead, maybe change your angle, right? Make that along that tangential force so that you don't have any radial force, pure tangential. So you're maximizing your force and it's perpendicular to R, then you will get the largest torque. So for a given R, the torque is largest when F is perpendicular to R. And the reason is because sine 90 is 1, that's the maximum for sine function. And for units, so how do we find the torque? We had rf sine theta. Sine theta has no units. R is meters and F is newtons, so we are using newtons meters, okay, or foot-pound. And again, we discussed this in work, and I told you then it was F dot D, so Ft cosine theta, that also has newtons meters, but we didn't keep it as newton meters, we kept it as joules because it was the work term, and work is a way to add or take away energy from the system, right? So now we are not going to use joules for torque, although it has the same dimensions as work, but it is going to be a different type of multiplication, and torque is a vector, work is not. Okay, so we are going to keep the units in terms of, in SI units, it's as newtons meters. And we're not going to call them joules, okay, because it's not energy. For one thing, energy is scalar, torque is going to be vector. Okay. And there is another way you can find the torque. So here we did split the components of force. You can also think of the components of R instead of the torque, instead of the force. Okay, so what we do here is you take the perpendicular R to F. So you extend the line of F. First of all, you can see this dashed line here. This is the force direction. That's the extended line. So you kind of take that force right here and find that line from the pivot point to the force point, but you're looking for this angle here, 90 degrees, okay? Because this angle is not 90 here. You're moving the force when you get that perpendicular distance, and this is R perpendicular, right? And you can use this triangle here, right triangle, and this is your angle because these two angles are the same. And so you can solve for torque this way. So R perpendicular is the perpendicular distance between the rotation axis and the line of action of force, F. And the distance is also called moment arm. And we see that in this case, torque is, we already know that it's RF sine theta. What is R sine theta? It is that perpendicular component, right? From this triangle. So this is theta here, and this is opposite is what we are looking for. R is the hypo, so you can use sine theta, and sine theta here is, let's just take a note of that. Opposite R perpendicular divided by R. So if you rewrite R perpendicular, it becomes R sine theta, so you can change that with R perpendicular, okay? So the torque can be written in terms of RF sine theta or R perpendicular times F. So you're not changing F, you're changing the perpendicular component of R. Or you keep R the same and take the perpendicular component of F, and it becomes FTR. So you have a kind of 3 different ways. They are all the same, okay? And to increase torque, one should increase R perpendicular and or F, right? So you're looking at what torque depends on. Above equation tells you what it depends on. And also note that the R perpendicular is largest when theta is 90 degrees. So we were looking at this angle because it was like large angle here. We get the 90 degrees, but then you shorten R. So if, again, this R and this F were perpendicular to each other, that would be even a bigger torque. And most importantly, torque is a vector. Okay, this is very important. Work done was scalar. It's a form of adding or subtracting energy from the system. But torque is a vector, it's not energy. The torque vector is perpendicular to both R and F and found by the right-hand rule. I started talking about the right-hand rule earlier, and we're going to do a lot of right-hand rule in the torque section. And how do we do that? And you will see that also written as RHR, right-hand rule. So what you do is you point the fingers of your right hand along the direction of R, okay, and curl them toward F. Your thumb points the direction of torque. So if you have R like this and F like that, I said that's R, not F, and this is F. So use your 4 fingers along R and curl them toward F, okay? You can also kind of carry that F over here, right, the same vector. So you're going from R to F with the 4 fingers, you're curling them towards F, and you can see that this is counterclockwise, and that is the torque direction, okay? And this is the direction of torque. Another way of saying this is your thumb is coming out of the page when you curl your fingers counterclockwise. And the magnitude of the torque is RF sine theta, and the direction is given by the right-hand rule. So torque is a vector, right-hand rule will give us the direction, and RF sine theta will give us the magnitude.